Hello everyone, today we will be doing the first chapter of IGCSE Physics, which is Motion, Forces and Energy. We will be doing this chapter in 4 parts, and today we will be doing part 1, which is 1.1 Physical Quantities and Measurement Techniques, and 1.2, which is Motion. Now let's start with our first part. Physical quantity is basically any quantity that can be measured. Before measurement can be made, a standard or unit must be chosen. There are 3 basic quantities in physics, which is length. Let me write that down. Length, which has a unit meter represented as m, mass, which has the unit gram represented as g, and time, which has a unit second represented as s. All the other quantities are derived from these 3. So stuff like force, which has the unit newton, it is derived from these 3, and all the other ones too. Force was just an example. Okay. Before we move on to their land, mass, times, units, and measurement techniques, but first we need to know about metric prefixes. So all the stuff like kilo, centi, milli, micro, nano, these are all metric prefixes. And their purpose is simple. It's just to modify a base unit to make it larger or smaller by the powers of 10. So we have kilo, which is represented as K, which is 1,000 times larger than our base. There's centi, represented as C, which is 100 times smaller than base. So for example, just to keep stuff simpler, we can make meter our base. Okay? So 1 kilometer is equal to 1,000 meters, which you can also write as 10 to the power 3 meters. Okay? Then comes 1 meter is equal to 10 decimeter. Actually, let's note all the stuff we know. Deci, D, kilo. Okay, let's move this up actually, because here comes our base. Okay, then centi, C, milli, M, micro. This is the sign used for micro, okay? And then nano, N. So this is equal to this much. 1 meter equal to 100 centimeter. 1,000 millimeter, which is equal to 10 to the power 3 millimeter. And 10 to the power 6 micrometer, which is around a million. Okay? And 1 meter is equal to 10 to the power 9 nanometer. These are stuff that you need to know. Next, we have length. Its unit is meter, represented as m, as we discussed earlier. And its measurement techniques. First, obviously, you can measure from ruler or meter rule. And it is used to measure lengths of tens of centimeter. Okay? And then we have spindle wheel, which is used to measure lengths of tens of meter, not centimeter. Okay? Now 3 and 4 aren't exactly in our syllabus, and it's also new to you, but it will be helpful to know what it is, as you can use it in your P6. Micrometer screw gauge. I might attach a picture of it. Okay. Micrometer screw gauge is basically to measure very small dimensions. It can measure up to like with accuracy of around 0.01. 0.1 millimeter. Okay, and examples of why it can be used is for thickness of paper, such thin stuff. Okay, or a diameter of a wire. Okay, then we have vernier caliper, and it's used to measure linear dimensions of objects like a ball or a screw. Here, let me add a picture of it, and then you will understand. Here. So you can see over here, this part will measure the outer dimensions, and then this thing can measure the inner dimension of something. Do you get what it means? Now, again, as I mentioned earlier, the 3 and 4 are not exactly in your syllabus, so it's not important to know how to use them, etc. But it will be helpful to know where you can use them, because that can be used in your P6. Another thing, while measuring from a ruler, it is important to avoid this one error, which is called parallax error, which you can avoid by looking perpendicular to the ruler. Let me attach a picture to show. Here. If you look perpendicular, you will be able to see the exact thing, right? Or else you can see if you look at the ruler, bro. If you look at the ruler from different angles, then they're misreading it. It's 6.2, but if you look at it from here, it will be 6.5, 6.0. So for your accuracy, you have to look perpendicular to the ruler. And this is a measurement inaccuracy. Always. Okay, so now we know it's a measurement inaccuracy. We're moving on to area and volume calculations. First, we have area. So area's unit is meter square, and we'll be talking about different formulas to calculate area. So area of square, x into x is equal to x square, or you can say like length. Here you can see this is x and this is x. Okay, and then area of rectangle would be length into breadth. We can say L into B. Okay, this is length and this is breadth. Okay, then we have area of circle, and it's formula is pi r square. Pi is a constant value. It's also in your calculator, but its first 3 digits are 3.14. Okay, and it's a very long number. Okay, r is the radius of the circle. Like, okay. Now moving on to volume. Volume's unit is meter cube, and volume is basically the amount of space occupied by an object. Okay. Okay. Volume of cylinder here is pi r square h. Okay. This you can. Oops. Just like this, it's a cylinder, right? This is the h, and this is over here. This part is r. Okay. Then we have volume of sphere. Its formula is 4/3 pi r cube. Here it is, r. Okay. Then volume of cube, it is L cube. So if this is a cube, right, this part is its length, because obviously all the dimensions are equal for a cube. For a cuboid, it is length into breadth, or you can say width into height. So L into B into H. Sorry, into H. So it's like this. Okay. For measuring the volume of liquid now, volume of liquid. Sorry. We use measuring cylinders. And again, for measuring cylinders too, you have to look perpendicular to avoid parallax error here too. First of all, in this picture, you can see you have to look perpendicular to, or else you will mismeasure. You have a measurement accuracy, sorry. And the other thing you have to make sure is if the liquid is of a concave shape, this is con, then you will have to look at the lower meniscus. Okay. And if it is a convex shape like this, then you will have to look at the upper meniscus. Basically, you can even notice that whichever part is the curved part, you just have to take the readings from there. Okay, now we are done with area, volume. Next we have time. Yeah. Time has a unit, seconds, represented as S, and yeah, you can measure time using stopwatches. One thing for time you have to note down is the human reaction time. You have to take this in consideration while doing an experiment, which is 0.25 seconds. Okay, basically it's how much time a human takes to react. So for example, you have a pendulum and you have to calculate the time taken for one oscillation. You won't be able to stop exactly. One oscillation will be from here till here and then back here. Okay, you won't be able to stop exactly at the time it stops here, right? That's why we take multiple readings. And it's not only for time, this is also for other measurements. You take multiple readings. So instead of taking the time taken for one oscillation, you will take time taken for 5, and then divide the time by 5 to get the time taken for one oscillation, which is the time t. Okay. Same goes for if you want to, for example, calculate thickness of paper. instead of measuring for one sheet, you can measure thickness of 100 sheets of paper, and then divide that length with 100 to get for one sheet of paper. This we do to reduce the impact of measurement errors and for more accuracy. Now we will be talking about scalar and vector quantities. Scalar and vector. A scalar quantity is a quantity which only has magnitude. It does not have direction, okay? And a vector quantity has both magnitude and direction. Okay, here are the examples of scalar and vector. These are all the examples of scalar quantities, and these are all the examples of vector quantities. You can see over here, the ones we'll be talking about mostly will be distance versus displacement and speed versus velocity, okay? First, we'll be talking about distance versus displacement. Okay, distance is the measure of how far an object has traveled regardless of the direction, which is basically the total length of the path taken, okay? And displacement is measure of how far 2 points are, including direction. So length and direction of a straight line drawn from starting point to the finishing point. Here, let me draw an example for you. Let's say this is your house, okay? And this is your school. Okay. Now, the road you take from house to school is this, okay? Sorry. This is the path you take. You have to go like this, okay? This is how you went to school. This is the road. But, so this thing is the distance. And this thing would be displacement. For distance, it won't matter if you're going from house to school or from school to house. It will be the same. But for displacement, it would matter. If this much is, let's say, 2 meter, just 2 kilometer for an example, okay? This thing would be minus 2 kilometer because it's in the opposite direction. And for displacement, for distance, it won't matter if you go from house to school, if you take the same path. Let's say it's 40 kilometer. Oh, I'm sorry, 13 kilometer. Actually, 40 is so much. 13 kilometer. Then, this path you have taken won't matter that much. It would matter, but it won't matter if you're going from school to house or house to school. It will still be 13 kilometer because you're not looking at a direction, okay? Next, we have speed versus velocity. Speed is measure of distance traveled by an object per unit time. So speed is distance over time. But velocity is the measure of displacement traveled by an object per unit time. Okay? And speed has only magnitude. This velocity will have both m and direction. Okay, like magnitude and direction. Next thing we'll be talking about is calculating resultant velocities. Vectors, not velocities, I'm sorry. Resultant vectors. Calculating resultant vectors. First thing you need to know is vector diagrams. You represent vectors with an arrow, okay? So let me draw an arrow. Okay? This length of the arrow is the magnitude. And wherever the arrow is pointing would be direction. So if a car is going this way, this would be its direction. And this way, it's all like different, okay? How can you calculate vectors, the resultant vectors? First method is calculating vectors using Pythagoras theorem. Okay, you have to do it graphically, okay? Using Pythagoras. Okay, as you can see here, this is a graph. This is our graph, right? This is the vector, okay? This is the vector we have. And we can take its vertical and horizontal components. This will be the vertical component, and this would be the horizontal component. And this would be the direction. This is the horizontal, and then this is the vertical. The magnitude for the vertical is 5, and the magnitude of the horizontal is 7 Newton over here. You can see from here 7 and this is 5, right? Now we can use Pythagoras theorem because we know a square plus b square is equal to c square. So we can do 5 square plus 7 square is equal to f square, and then 25 plus 49 equals to f square, and then you can get the value of our resultant vector. This method can be used when both vertical and horizontal components are given. Okay, basically two components that are in right angles to each other. These two are given. This thing is called the head to tail rule. We can know that since first this is the, you draw it like this, okay, this is the head of the arrow, right? You join the tail of the second arrow and join the head like this, and then you take the tail of the first arrow and the head of the second arrow and join it like this. So this will be the direction of the final vector, resultant vector. Second way is using SOH CAH TOA. So we have a triangle, okay? This is our angle theta. This is our resultant, this thing, okay? Which is hypotenuse. Hypotenuse. You must have learned this in maths by now, actually. This is F vertical, and this is horizontal. This is opposite, this is opposite to our angle theta, and this is adjacent. Okay, so O, A, H, remember this. So means, first we'll do so. Sine theta is equal to opposite over hypotenuse. So you can use algebra and we can get, since we have to calculate the value of hypotenuse, which is our resultant, right? What we do is, you move this hypotenuse over here, and this sine over here. So you get hypotenuse is equal to opposite over sine theta. That's how you can use, okay? Next we have CAH. So CAH TOA. So this is cos. Cos theta is equal to, since it's a adjacent, over hypotenuse. So H equals to adjacent over cos theta. These cos and sine values are in your calculator, so you just use those, okay? And then for TOA, it's not really helpful in this matter that much, unless you want to calculate the angle, okay? Because you're not really getting hypotenuse directly from this, right? You have the opposite and adjacent. It's better to just do Pythagoras theorem for the resultant vector. But just for information, let's do this too. So it's tan theta is equal to opposite over adjacent. And again, it's not exactly useful because resultant is hypotenuse. Now we can, we're done with SOH CAH TOA, but yeah, this sine theta can be used when angle and its opposite are known, okay? And cos theta can be used when angle and its adjacent are known. Let's, for example, we know this angle, okay? Also, this is right angle, just by the way, obviously. If we know this angle, okay, then its opposite will be FH, and its adjacent will be FV, the vertical component, right? So keep that in mind too. Now we are done with 1.1, which is physical quantity and measurement techniques. We're done with that. We will be moving on to 1.2 now, which is motion. Now we'll be starting 1.2 motion. We'll be talking about speed and velocity and acceleration in more detail than earlier. Okay, so speed. Speed of an object is the distance traveled per unit time. And its unit, unit is meter per second. Or you can write it as meter per second, like this, okay? Now, the formula is V is equal to S over T. V is speed, S is distance, and T is time. Here, you need to know how to use these triangles, okay? Formula triangles. So, it's like this. Since we want to find out what is V, which is speed, so we will cover this up, and S over T, S divided by T, then we will get velocity. I mean speed for now, okay? And if you want to find out distance, it will be V, see this, into time. Speed into time will give us a distance. And for time, we will do S over V and we will get time. It's sort of just like basic algebra, right? Next, average speed. Average speed is the total distance covered by an object per unit total time taken. And its formula will be total distance traveled divided by total time taken. That will be your average speed. Next is velocity. Velocity, we all know, is a vector quantity. Speed is the scalar quantity. Velocity, again, velocity of an object is the displacement traveled per unit time. Displacement traveled per unit time. Okay, and velocity is speed in a given direction. Okay, you also have to remember that. Formula for velocity is equal to displacement over time, or you can say V is equal to S over T, but in this case S is displacement and V is velocity. So for magnitude of, for velocity, its direction can be given in words or by positive or negative. Okay, for words, let me give an example. So for example, you are traveling 20 meters per second in the direction of east. Okay, so this is the velocity. Or it can be given with positive or negative signs. Okay, how? Let me show you. So for example, there is a ball and it goes in this direction and its speed here is 5 meters per second. This will be positive. Okay, there is other ball that is going in the other direction with speed 3 meters per second. So this will be negative because it's in the opposite direction. So V2 will be negative, opposite direction. That's why it will be negative. Next we have acceleration. Acceleration is rate of change of velocity. Its formula will be change in velocity over change in time, or you can say V2 minus V1 divided by T2 minus T1, as in and its unit is meter per second square, or you can also write it as meter per second square like this. Okay, and also for this unit is also meter per second square, the same as that of speed. For velocity it's the same as speed. Moving on, again you can also use the triangle thing here, by the way. When there is any change in velocity, if it speed up, if a car for example speeds up, that will be positive acceleration, and if it slows down, it will be known as deceleration. Deceleration is basically negative. No, the hell, deceleration is negative acceleration is called deceleration. Then we'll be talking about distance time graphs and velocity time graphs. Now we'll be talking about distance time graphs and velocity time graphs. Okay, here is distance time graph. Okay, distance in the y-axis and time in the x-axis. When there is constant speed, that graph will show a straight line. Okay, and if it's a steeper slope like this one, steeper slope, then that means the speed is higher, the value of speed will be higher. Okay, and if it's a shallower graph, that means the speed will be smaller. And yes, here when the speed is increasing slowly, as in accelerating, then the graph will be like this. When it's decreasing, the graph will be like this. These are all stuff you need to remember, by the way. Okay, for when the car or object is at rest, it will be like this, because obviously the distance won't increase or decrease since it's not moving. Next we have, how can we, one thing you need to know, the next thing you need to know is that gradient of distance time graph will give you speed. Okay, so let's say you will have to calculate speed of this car. This is a graph of a car traveling. Okay, and you have to calculate the speed of the car. As you can see, it's right now the graph looks like this. That means it's a constant speed, right? So you just take the gradient. Gradient will be y2 minus y1 over x2 minus x1. Let's take 2 points. Okay, one will be 0 0 because you can see it's at origin, and the other point will be 3 2, this point. Okay, now how you'll do this is, let's make this is x1 y1 x2 y2. So 2 minus 0 divided by 3 minus 0, you will get 2 over 3, which is equal to 0.75, I think. Let me check that actually with the calculator. No, it's actually, sorry, which is 0.667. Next, we'll be doing velocity time graph. For velocity time graph, when there is constant acceleration, then the line is straight. Okay, this means it's constant acceleration. And obviously, if there is more acceleration, it will be like this. If it's the value of acceleration is smaller acceleration, then it will be like this. Okay, but remember, the acceleration is constant. When the velocity is constant, this is what the graph will look like. For velocity time graph, this is constant velocity, because obviously, if this is 2, that means the speed has been 2 for a long time. Okay, but for distance time graph, this is what constant velocity looks like. Constant speed, sorry, this is constant speed looks like. Okay. Next is constant deceleration. This was acceleration, this is deceleration. As I mentioned earlier, deceleration is just negative acceleration. Also, for velocity time graphs, the gradient is acceleration. So as you can see here, gradient is negative, right? So it will be deceleration. Next is increasing acceleration. This will be increasing acceleration. This will be decreasing acceleration. And obviously the same thing but negative, this will be increasing deceleration, because it's negative, and then this will be decreasing deceleration. Now let's learn how to calculate the gradient again for acceleration. Again, the same thing. You take the points, you get the gradient, and this will be your acceleration. Next thing we need to know is that the area under the graph of velocity time graph, area under the graph of velocity time graph will be your displacement, or like actually distance will be the distance covered. Sorry, not displacement, distance covered. Okay, so as you can see over here, this is why you need to know the area of triangle, area of rectangle, etc. So this is our example. This is our velocity time graph, right? You can either calculate the area of this as a whole trapezium, or you can divide it into 2 parts and calculate the area of triangle first, and then rectangle, and then add these both together to get the total area. This is pretty simple. I won't be doing further explanation. You can just look at the working here. Right, now we'll be moving on. Next is another thing they can ask you is how can you calculate the volume, gradient, the acceleration of a curved graph. That is simply by making a tangent. So they can ask you that calculate the acceleration of the car at 1 meter per second. So you will make this here. Okay, you will make a tangent here. Take a ruler and make a line, straight line going like this. Okay, then you can calculate the gradient of this line by taking multiple points, right? You can get the gradient. These are the formulas for areas of triangle, rectangle, and trapeziums. I can note that down too. Now we have the last topic left, which is free fall. Free fall. Okay, free fall is basically if an object were to fall from height in a vacuum, which is a space with no matter or particles whatsoever, it would experience no air resistance and therefore would constantly accelerate till it reaches the ground. So for an object, W is equal to mg. Okay, W is weight. Weight in Newton. It's a force. Okay, W is a force. Okay, as you can see, it's in Newton. Okay, mass is m. Sorry, it's g, and g is gravitational field strength. Gravitational field strength, which has a unit Newton per kg. Okay, and mass is in kg. Sorry. Okay, so from Newton's second law, we know F is equal to ma, and F is force, m is mass, and a is acceleration. Okay. Then we can say A is equal to F over m, and A is equal to F mg over m, because W is a force, weight is a force. So F is equal to W and W is equal to mg. So you can just displace that here, right? Then you get, cancel this both, you get A is equal to g. So our acceleration in free fall will be gravitational field strength, and the value of gravitational field strength is in Earth is 9.81. Each planet has their own different gravitational field strength. So that means if, let's say, heavy metal, or let's say a hammer, if a hammer or a feather both were to fall from the same height, let's say 20 meters, okay, in a vacuum, which is a space with no air, no particles, okay, in a vacuum, they both will fall at the same acceleration, which is 9.81 meter per second square. Okay, they both will fall at this in Earth. Okay, in other planets the acceleration will be different, but when we're talking about in Earth, it's going to be 9.81. And I think in your syllabus you just have to know 9.8 maybe. Yeah. Okay, they both will fall at the same time and will land on the ground at the same time. Okay, this is without air resistance. This is free fall which is falling off an object in a vacuum. Now we'll be talking about falling object with air resistance. Okay, falling objects with air resistance. Okay, so let's say our falling object is a ball. Okay, so at first the object will start to fall, air resistance will be 0, and acceleration will be maximum. So there will be a large resultant force, and resultant force will be downwards, right? Then as it starts to fall, slowly the air resistance starts to increase. So the acceleration starts decreasing. You can say over here, if this is the force in the beginning, and then this is your weight force, right? And slowly air resistance starts increasing. Weight will stay the same, but because of that the resultant force will obviously decrease a bit. And then it reaches terminal velocity, which means that air resistance is equal to your resultant force. So this is what will happen. Both will be equal. So you will reach terminal velocity, meaning acceleration is equal to 0. So if you were to draw a graph on this, it will look like this. This will be its velocity time graph. Okay, this is how the graph would look. Sorry. See, in the beginning over here, this is steepest, right? So acceleration is maximum here. Max acceleration. And then slowly you can see acceleration slowly decreasing because the air resistance is increasing. And over here, terminal velocity has reached, meaning there is 0 acceleration and constant velocity, right? Now what happens when a skydiver is falling? How air resistance works on a skydiver. How air resistance works on a skydiver. So for a skydiver, first of all, the skydiver falls. Okay, so first of all, the object falls, and sorry, not the object, the skydiver falls, and initially resultant force large. Okay, it's a large value. Okay, I think it'll be the highest right now. Okay, and then acceleration, the first 3 steps will be the same as earlier. Okay, is gonna be max. Air resistance 0. Then as they fall, air resistance increases, and so acceleration slowly decreases. Okay, then terminal velocity as earlier is reached. Okay, just this all is these 3 steps are the same here too. But then after terminal velocity is reached, the skydiver opens the parachute. So parachute opens. As soon as the parachute opens, first the skydiver will experience deceleration. Okay, because air resistance is more. As soon as the parachute opens, air resistance is more than acceleration. It will be more than downward force, or you can say weight. Like this. Let me show you. Air resistance is more than this. That's why immediately they will experience deceleration, which is negative acceleration, and then a new slower terminal velocity is reached. So that means air resistance is equal to resultant force. So acceleration will be 0. Velocity will be constant. Let me draw the graph for this now. Okay, this is how the graph for this would look like. First part would be the same like this. Sorry. But then after this has reached, this is what will happen. Okay. At the very beginning, the velocity, the acceleration maximum, because look, it's the steepest. Then acceleration slowly decreases. Okay. Then over here at step 3, terminal velocity. And at this point, parachute opens. So here you can see deceleration occurs, because the air resistance is higher than the result. The air resistance is higher, like more than the resultant force. Okay, that's why. And then another terminal velocity reached. Terminal velocity reached, and that's how the skydiver will safely reach the ground. So everyone, since some of you might not have enough time to watch the full video, here is a quick 5-minute summary. Okay, so before measurement can be made, a standard or unit must be chosen. And in physics, we have three basic quantities. Which is length, which has a unit meter represented as m, mass, which has unit gram represented as g, and time, which has unit seconds represented as s. There are metric prefixes: kilometer, decimeter, centimeter, millimeter, micrometer, nanometer. These are all metric prefixes, and their purpose is to simply modify a base unit to make it larger or smaller by powers of 10. Here we have used meter as an example for our base, but in other cases, there can also be kilogram, etc., etc. Okay, so here kilo, deci, centi, milli, micro, and nano are examples of them. Here is a quick small chart you can look at to know how much each is equal to. We have only used meter as an example here. Okay, this can also be for gram, etc. Okay, next we have length. Length has a unit meter, and here are its 4 measurement techniques. First is a ruler or meter rule, which can measure tens of centimeter; Trundle wheel, which can measure tens of meters; and micrometer screw gauge, which can measure very, very small dimensions like thickness of paper or a wire. Here is a picture of micrometer screw gauge, just for example, just so you can see. And micrometer screw gauge is not in our syllabus, so you don't need to know the details. And same for vernier caliper, it's not in our syllabus, so no need to know details. But this can measure the inner and outer dimensions of different linear dimensions of different stuff, like even a ball, etc. So this can measure the outer dimensions. This can measure the inner dimension. So you can put this over here and measure it like this. You get what I mean? Okay, done. Next, yeah, parallax error. It is a measurement inaccuracy which happens if you don't look perpendicular to this. So if you are looking at different angles, you can misread it. You see? That's why it's very important to always, while taking any measurement, to look perpendicular to the ruler, etc. Now, area. Area has a unit meter square, and these are the formulas of area. For a square, it's x square. For a rectangle, it's length into breadth. For a circle, it's pi r square. R is the radius and pi is 3.14, value in our calculator. Okay. Volume. Volume has the unit meter cube, and here are the formulas of volume. Cylinder's volume is pi r square h. Sphere's volume is 4/3 pi r cube. Cube's volume is length. Length into length into length, or even say length to the power of 3. Then you have cuboid volume, which is length into breadth into height, as you can see here. Okay, for a volume of a liquid, you use a measuring cylinder. Okay, and again, you have to avoid parallax error even for the volume of a liquid, so look perpendicular, not at different angles. Another thing you have to make sure and note down is, for a measuring cylinder, if it's of a concave shape, you have to look at the lower meniscus. Okay, and if it's a convex shape, then upper meniscus. Okay, as you can see here, upper, lower, whichever part is curved, basically you have to look at it over there. Okay, next we have time. Times unit, oh sorry, this is wrong. Times unit is seconds in s. Okay, and you can measure it by stopwatch. An important factor while measuring time you have to make sure is about the human reaction time, which is 0.25 seconds. So to avoid that, we take multiple readings. For example, if you want to take time of an oscillation, instead of taking off one oscillation, you let the pendulum oscillate, let's say 5 times, and then divide that time taken by 5 to get the time taken for one reading. So you take multiple readings to reduce impact of measurement errors. You can also do that with other stuff, not only time. For example, for length, you can take the length of 100 sheets of paper instead of one, and then dividing that length with 100 to get the length of the thickness of one paper. Sorry. Okay, moving on. Scalar and vector. Scalar is a quantity with magnitude only. Vector is a quantity with both magnitude and direction. Here are the examples of scalar and vector: distance, speed, mass, all of these, etc. Okay, even these you can take a look at it. The ones we will be talking more about will be distance and displacement, and speed versus velocity. Okay, next. Distance versus speed. Distance is the measure of how far an object has traveled, regardless of direction, while displacement is measure of how far 2 points are, including direction. So, just a visual example here. You can see for going from point A to point B. This is the path you took for going from A to B. It won't matter if you go from A to B or B to A, the distance will be the same. But for displacement, first of all, displacement is going to be just a straight line from A to B, okay? And it wouldn't matter if you go from A to B. For example, if you go from A to B, the value will be in positive. But if you go from B to A, which is the opposite direction, it will be negative. Quite simple, isn't it? Okay. Now you have calculating resultant vectors. First of all, you represent a vector by an arrow. The length of the arrow is the magnitude, and the direction of the arrow is obviously the direction. Wherever the arrow is pointing is the direction, okay? So now you can calculate resultant vectors by these two following ways. First of all, Pythagoras theorem. See, this is a graph, right? And this is our resultant force, okay? Resultant vector or whatever, okay? Now, let's say its points, this is 5, 7, right? That means this length is 5 Newton and this length is 7 Newton. So you follow the head to tail rule, which means that, oh wait, I actually noted it down. This is 5 Newton and this is 7 Newton. Anyways, so head to tail rule is basically at the head, which means the arrow of one of the vectors, you put the tail of the other vector and draw it out. And then you join the first tail to the final head. That will make your resultant vector. And then you obviously, Pythagoras theorem is a squared plus b squared equals to c squared. So you do that and you get your answer. The other way is SOH CAH TOA, which you must have done in maths. So this is a right angle triangle, okay? And this is our angle theta, which is known, okay? Our angle theta is known. Opposite to it is this, and adjacent to it is this. This part is called the hypotenuse. We want to calculate the hypotenuse, which is our resultant vector, right? A resultant vector, yeah. So what you do is simply sine theta. So means O means opposite, A means adjacent, H means hypotenuse. So means SOH. Sine theta is equal to opposite over hypotenuse, and for cos theta it means for CAH it means cos theta equals to adjacent over hypotenuse. And then you do your algebra and shift these both. Wait, you shift these both, and hypotenuse is x. Okay. Again you shift these both, and then you can get your answer. Okay. Next we are done with our 1.1. Now we'll be moving on to 1.2. So motion, speed. First we'll talk about speed. Speed is distance traveled per unit time. This is its formula. V equals to S over T. V is speed, S is distance, T is time. Average speed is the total distance traveled divided by total time taken. So yeah, velocity is displacement traveled per unit time. So this is the difference. This is distance traveled, this is displacement traveled, and you look at the directions here. Okay, in here you don't really look at the direction. So as you can see here, okay, this is again the same formula. Velocity, this is velocity, this is displacement, this is time. Okay, here for this it matters because look at this. This if you go from here to here, it'll be positive. If you go from here to here, it'll be negative. So this represents, these two represent the magnitude, and this positive or negative sign represents the direction. Next, acceleration. Acceleration is rate of change of velocity. This is its formula. You know, change in velocity over change in time. Simple. Next, we have distance time graphs and and velocity time graphs. Okay. So in distance time graph, this represents, when the line is straight, it represents a constant speed. Okay. This means the object is traveling in constant speed. This would be increasing speed if it's curved like this, and if it's curved like this, then it's decreasing speed. This thing is rest. For a distance time graph, the gradient of the, what do you call that? The gradient of the graph will give you your velocity. So you can calculate your gradient. Gradient is equal to y2 minus y1 over x2 minus x1. So you take 2 points from the graph, let's say 0, 0, and let's make this 3 and 2. Okay, so you can do 2 over 3, and that will be your answer, because 2, you can do 2 minus 0 over 3 minus 0, which is 2 over 3. That will be your velocity, just for example. Okay, another thing here for distance, not for distance, I mean for here, you can see if the slope is steeper, then it will be a larger speed, and if the slope is shallower, it will be a smaller speed. Velocity time graph. This, for velocity time graph, a straight line upwards would represent constant acceleration. A straight line downwards will represent constant deceleration. Deceleration is simply negative acceleration. For velocity time graph, the gradient would represent the acceleration, and area under the graph would represent distance. So they can, at times they would give you a graph and ask you to calculate a distance, or you just have to calculate the area under the graph. So for triangle, it will be half BH, which is the area. For, if, let's say for example, this is our graph, but our graph is like this, you can either calculate the area of a trapezium like this, or you can divide it in 2 parts. Okay, you can divide this thing in 2 parts and calculate the triangle first, and then the rectangle area, and then add it all together. That's how you can get the distance. Okay, then there is increasing acceleration, which is a curved graph like this. Decreasing acceleration is like this. Increasing deceleration is a curved graph downwards like this. Decreasing deceleration is this. They can also ask you to calculate the acceleration at a point. For example, for here they can ask you to calculate the acceleration at this point. So what you would do is you would draw a tangent and then calculate the gradient of this tangent. Okay, and that'll be your answer. Next we have free fall. Free fall is basically when an object falls in a vacuum. A vacuum is a space with no particles, no air whatsoever. So if an object were to fall in vacuum, this is what would happen. Its acceleration, okay, we know W is equal to mg. W is weight, this is mass, gravitational field strength. Okay, this is 9.81. Okay, F is equal to ma, force is equal to mass into acceleration. Then you can say A is equal to F over m, and since W, weight, and force are this, weight is a force. Okay, so we can say W is equal to F. So F is equal to mg, and then you cancel the m, you get g. So A is equal to g. That means that in a free fall, in a vacuum, the acceleration of any object would be the same, and it would be 9.8 in Earth. In Earth, the gravitational field strength is 9.8. So let's say if a heavy hammer was falling, or a feather was falling, they both will reach the ground at the same time, and if they fell from the same height. Okay. Now we'll be talking about air resistance on skydivers. Okay, so first of all, the skydiver falls. Initial resultant force is maximum, and acceleration is also maximum. But air resistance at the initial point is 0. Here, you can see this is the most steep, so air resistance is maximum. No, sorry, acceleration is maximum, and resultant force will also be maximum here. Then, second, air resistance slowly starts increasing, so acceleration starts decreasing. Over here, air resistance. This was force initially, there is no air resistance, okay? Slowly, air resistance starts to increase, okay? After that, over here, see? This is decreasing acceleration. Then, they reach terminal velocity, meaning there is no acceleration, and there is no resultant force. Air resistance and or downward force are equal, so velocity is constant. Then at this point your parachute will open and they will experience deceleration. Okay, the accelerations are slowly decreasing, as you can see here, and at this point air resistance will be more than force, so the parachuter might initially feel an upward force. Okay, and then they will start slowly coming down, right? And lastly there will be a new slower terminal velocity. So over here there will be a new slower terminal velocity. Again, velocity will be constant. That's it. So that's it. See you in the next video. Bye.